Hey guys, thanks for joining the lesson. We're going to be covering the topic of mechanical energy, specifically going to focus on work and kinetic energy. I will be doing some practice problems that you are going to need to know how to do similar practice problems for the quizzes and the test for this unit. So let's go ahead and jump into some of the topics. Here's some of the vocabulary that you are going to need to understand for this module, so let's go over them. The gravitational potential energy, which is mechanical energy due to the height of an object above the arbitrary 0 point. Kinetic energy is the mechanical energy due to the speed of an object. The law of conservation of energy is the energy cannot be created or destroyed, it can only be changed from one form to another. Mechanical energy. Mechanical energy is the energy due to position or motion. Power is the rate of energy transfer. Spring potential energy, which is the energy stored by the expansion or compression of a spring from its equilibrium position. And work, which is the energy transferred by applying a force on an object, causing it to move in the direction of the force. Work. Again, work is, went too fast, sorry. Work is a force that is being applied to an object and it moves in the direction of the force. We say that the force is done on the object. Work can be measured in joules, and remember the definition of joules is the energy transferred if 1 Newton is applied over a distance of 1 meters. Remember that energy is a scalar quantity, which means that it does not have to be given a direction when you are giving its answers. And if work is being done on an object, it is considered to gain energy, and as work is being done on another object, it actually is going to be considered to lose energy. Here are some of the formulas that are associated with work. So we have work equals force times distance. So this is going to be used when the force and displacement are in the same direction. We also have work equals Fx, which is cosine, which is going to be the direction of the horizontal force. And you can see that below you're going to see some more formulas as the module goes on, and some of those formulas can be found in the graphic. Work is done on an object only if the object moves, and this is something important to understand. So if some component of the force is in the direction of the motion. So here's an example. If a person does work by breathing air or pumping blood, but maybe the box isn't moving, then it's considered that no work is being done, even if the person pushes really hard. So the object, again, has to move in order for work to be done in the physics terminology. Also, again, if some component of the force is being in the direction of the motion. So if you're pushing on the box and it's moving towards or against the push, then that doesn't consider that work is being done on the object as well. Let's talk about the difference between negative versus positive work. And basically it is if the object is having work done to it and it slows down, then it is considered negative work. So here's an example. If a person lifts a weight over their head, the person does positive work on the box because the force of the motion are in the same direction, which is going to be up. But remember that gravity in the form of weight, which is pulling down on the box, does negative work on the box. So the weight is down and the motion is up. All right, so here is our first kind of example to calculate force. It's going to state a car with a mass of 2,000 kilograms coasts down a hill. I'm going to highlight some of the stuff as I'm reading it. Coasts down a hill that makes an angle of 30 degrees to the horizontal. The car is acted on by 3 forces. We again have the normal force, a 1,000 force of friction in the opposite direction of motion, weight, or also known as gravity, pulling down on the car. So we need to find the work done on each force and the total work done on the car as it travels at a distance of 25 meters down the slope. So the first thing we need to go back is think about a free body diagram, which you can see down here. So if this is the object, again we have the, let me get a different color since that's red down there. So we have the weight pulling down on the object. We have the force of friction pulling in the opposite direction of the motion. We have the direction of the motion, and I know it says gray down here, but it's more blue that I just drew. And then we also have the normal force. So the first thing we want to do is calculate the normal force. So how we do that is we can use the fx cosine formula. We plug in what we know, which is the 90 degrees and the weight of the force in the newtons, and we're going to get the weight N equals 0. Next is going to be the frictional force. So again, the frictional force is going to be that lowercase f. This is reviewing stuff that we covered last semester. The weight of the friction equals fx cosine theta. Work of the friction equals 1,000 times 25. The 1,000's coming from this number right here. The 25 was the distance. Again, x is the distance, which is what we're getting from right here in the problem. Cosine 180. We're doing 180 because it is 180 degrees from the force. If we plug those into our calculators, we should get negative 25,000 joules. And again, since we just calculated the normal weight force, we plus the weight force of the friction, so that's going to be 0 minus negative 25,000. So our answer is negative 25,000 joules, and we know that it's negative, and that checks out because friction is always in the opposite direction of the motion. Part C, or that last part, with the same problem that we were just working with, first you're going to have to find work done. First you're going to think about the angle that's between the weight and the incline that can be shown as 60 degrees using geometry. So we know that it's 60 degrees because in the problem it's given 30 degrees, and 30 plus 60 would be 90, so that's our right angle. So then we plug in what we know. We have the mass in the problem, which is 2,000. Gravity, we know that as 9.8, that's a constant. 35, which is what we calculated before, and the cosine 60. We plug in those to our calculator, and we get 343,000 joules. We put all the work forces of all three of the works that we were talking about in the original problem together, so 0 plus negative 25,000 plus 343,000, and our final answer for all of the work being done in this one problem would be 368,000 joules. All right, let's talk a little bit about the work kinetic energy theorem. So if we spend some time relating force and mass to the kinematic equation, we can determine that Fx equals 1/2 mv, mass times velocity squared, minus 1/2 mv of the second object squared. So we combine this with our definition of work, and we can get this formula below. So we have the work equals 1/2 mass velocity squared minus 1/2 mass velocity squared of the second object. This is actually called the work kinetic energy theorem. So now focusing on kinetic energy. Remember again that the kinetic energy is a scalar measurement, so direction does not matter. So you do not have to put a direction when answering questions asking for kinetic energy. The formula of kinetic energy is, you can see it right here. Kinetic energy equals 1/2 times mass velocity squared. So the kinetic energy is the energy of the object due to its velocity. In reality, because energy is scalar, not a vector, all that matters is the magnitude of the velocity, or the spin. All right, so for our first practice problem for kinetic energy, it states a 45 kilogram box is moving at 3.00 meters per second. It's asking what is the kinetic energy of the box. So we use our simple kinetic energy equation, plug in what we know. We have 1/2 times 45, which is the mass, which is given to us in the problem, times 3, which is the distance, or excuse me, not the distance, the velocity. So 3.00 meters per second. We're going to square that. We put that into the calculator, and because of sig figs, we are going to get 202 joules. Part B of the same problem, again, a 45 kilogram box is moving at 3.00 meters per second. This time it is asking if a force of 75 newtons is applied at an angle of 55 degrees for a distance of 10 meters, how much work is done on the box. So since it's talking about an angle and not at a horizontal, we're going to have to use this equation, work equals Fx cosine theta, typo there, theta. So we're going to plug in what we know. We have the force, which is given to us in the problem, 75, 0 newtons, times 10, which is the distance, and that's what x is. Cosine, make sure your calculator is in the right mode. 55 degrees. We plug that into our calculators, and we should get 430 joules. And again, you have the decimal indicating the significant figures in that answer in order to get the full credit for it. All right, another question that could be asked about a simple problem is a 45 kilogram box is moving at 3.00 meters per second. Now it's going to ask us what the final velocity of the box is. So remember the theorem that we talked about previously, that formula. Remember, we have actually already calculated work in the initial kinetic energy. So basically, since we got it from the previous part of the problem, we're going to put 430 equals 1/2 mass velocity squared minus 202, which also we calculated. We're going to simplify what we know. 430 equals 1/2 45 velocity squared minus 202. Again, simplifying those values further. 202. Now we can move the velocity squared on one side. And remember to take the square root, or to do the reverse, we're going to take the square root of the entire side. 430 plus 202. Make sure that's in parentheses, that we do that before dividing 22.5. If we follow all of those steps correctly, we should get 5.30 meters per second as our final velocity. I went ahead of myself here. All right, we can also use a graph to help us answer some of these problems. It says, what is the work done on the object from 0 to 4 seconds? So first we're going to have to find the area of the object in our graph. Use the formula work equals 1/2 x versus force times distance. And we should get 1/2 55 times 4 equals 110 joules. So again, the 55 is coming from the point of our graph, and the 4 is coming from the displacement, the meters down below. Another question is, what is the work done on the object from 4 seconds to 10 seconds? So we look at 4 seconds to 10 seconds. So we're going to find the area, again using that same formula, 1/2 55. So that's at that 4 times 10 minus 4, because that's going to be the displacement covered in that time period, and we should get 165 joules. Another one is, what is the object being done on the object? Sorry, I think I had a little delay in the video, so I might be repeating myself just a little bit. But the last part of this problem is asking what the total work done on the object would be. And all you do is simply add the two works that you calculated on the previous two parts of the question. So that was 110. You add it to 165, and you will get 275 joules. All right, here's another type of question. It says, if the object has a mass of 15.0 kilograms and starts from rest, what is the final velocity? So we can use the formula that we talked about, the theorem. And we now know that initial velocity is 0 because it says that it's starting from rest. So you can eliminate that initial velocity part of the equation because it's going to be 0 and cancel out anyways. Plug in what we know for that final velocity. And so we're solving for it down here. We remember to take the square root of that entire side after moving around those numbers, and we're going to get 6.06 meters per second for the final velocity. And that is it for work and kinetic energy. Make sure to watch the second part, which is going to be focused on potential energy as well.